Hello friends, in the year 1988, two American scientists published a paper titled Numerical Evidence that the Motion of Pluto is Chaotic. In this paper, they clearly claimed that due to Pluto's chaotic orbit, the orbits of other planets in our solar system could be disrupted. To verify this, I personally tested their claim using a simulation software, and just look at what we found. There are 2 points in Pluto's path where it appears to intersect Neptune's orbit. That means if both planets were to arrive at those intersection points at the exact same time, a collision would be inevitable. Now mind you, this wouldn't be a minor collision. It would trigger a chain reaction that could reset our entire solar system back to square one. Just to give you an idea, after such a collision, all that would remain is the sun, surrounded by the debris of what once were planets. And I'm not even exaggerating. This scenario is like a ticking time bomb. But instead of panicking, let's calmly and rationally analyze the situation. Let's calculate if such a collision is even possible, and if it is, how strong and devastating it could really be. Let's start with the simulation that convinced you Pluto would collide. At first glance, in 2 dimensions, Pluto's orbit seems to cut through Neptune's, but in 3 dimensions, it becomes clear that Pluto's orbit is highly tilted, about 17 degrees compared to the other planets. And if you look closely, it doesn't actually intersect Neptune's orbit anywhere in 3-dimensional space. Secondly, even when Pluto and Neptune are at their closest, they are still 2.5 astronomical units apart. That's 2.5 times the distance between the Earth and the Sun. So, chances of an actual collision? Virtually zero. This proves that Pluto and Neptune are not going to crash into each other. But hold up, someone might still question these numbers. After all, we've never observed Pluto's full orbit since its discovery. So how can we know so precisely about its orbit? Well, to study a planet's orbit, we don't need to observe its full revolution. If we know a planet's mass and angular velocity, we can derive its orbit using physics. Thanks to the laws of planetary motion by German mathematician and astronomer Johannes Kepler published his 3 laws of planetary motion in the 17th century. These laws still allow us to analyze the paths of celestial objects with remarkable accuracy. Let me break them down simply. Kepler's first law. All planets revolve around the sun in an elliptical path. At Kepler's time, most astronomers believed orbits were circular, but Kepler proved mathematically and observationally that orbits are elliptical, with the sun at one of the foci. Kepler's second law. A planet sweeps out equal areas in equal intervals of time in its orbit. That means a planet moves faster when it's closer to the sun, and slower when it's farther. Imagine drawing triangles between the planet's position and the sun over equal time intervals. The area of these triangles will always be the same, regardless of distance. Kepler's third law. The time a planet takes to complete one revolution is directly proportional to the size of its orbit's semi-major axis. So using this formula, we can predict the orbital shape of a planet like Earth, just by knowing its mass and orbital period around the sun. So now, maybe you'll believe me when I say that Pluto isn't going to collide with Neptune, and there's not going to be any chain reaction wiping out the solar system. Kepler's laws give us a solid reason to relax. But wait, here's an interesting twist. Scene 3. Mercury's distance experiment. In 2009, 2 scientists tried using Kepler's laws to simulate the solar system's orbital evolution for 5 billion years. They made only one small change, reducing the distance between the Sun and Mercury by just 1 millimeter. Now what do you think happened? Probably nothing, right? After all, it's just 1 millimeter. But guess what? That tiny change turned the entire solar system chaotic. Mercury started falling into the sun, or colliding with Venus, or causing massive chain reactions that led to the inner planets destroying each other. So what does this mean? It means that Kepler's laws are great for short intervals, but don't work perfectly for long timescales. Are Kepler's laws wrong then? Not exactly. See, Kepler designed his laws for what's called the two-body problem. Interactions between just 2 objects like the sun and Earth or Earth and the moon. When more than 2 bodies are involved, like in our full solar system, things get extremely complicated and unpredictable. Let's understand this with a simple experiment. You've seen a pendulum, right? If I release it from one end, we can easily predict its path, speed, and energy. Now imagine I attach another pendulum to the bottom of the first one. When I release it the same way, the second pendulum's movement becomes completely chaotic and impossible to predict. This is exactly what happens in space too. Scene 4. The 3-body problem. When you consider 3 or more celestial bodies, their gravitational influences make the system so complex that accurate prediction becomes nearly impossible. This is what physics calls the 3-body problem. one of the biggest unsolved mysteries in physics. That's why, even today, scientists can't perfectly simulate the entire solar system over billions of years. We can only get accurate results when analyzing one planet at a time relative to the Sun. But the reality is, the solar system isn't just two bodies, it contains billions of objects, including asteroids and comets in the Kuiper Belt and Oort cloud. So when we can't even predict the motion of three celestial bodies with certainty, simulating the entire solar system accurately is nearly impossible. Still, for short durations, Kepler's laws work really well, and they are the reason why we've successfully sent satellites and missions to multiple planets.